Before we can talk about the technique of partial fraction decomposition, let's talk about what it's used for. Many times we find ourselves wanting to integrate a rational function. Remember that a rational function is a ratio of a polynomial over a polynomial. This is by analogy to rational numbers. A rational number is a ratio of an integer over an integer that gives us the rational numbers or the fractions. So rational functions are a ratio of the kinds of functions that kind of play a similar role to integers in this context. So, for example, let's look at the integral of the function 3x to the fifth plus 1/2 x cubed minus 8, all of that over the function 14x squared minus 6x plus pi times dx. Well, we don't even know where to start here. We have no idea. The only thing that you might think of here is, well, can I use some algebra to simplify it? Probably not. Neither of these polynomials seems to be something you can factor. If you can't factor it, then you can't simplify a ratio or a quotient of it. Remember, you can't just cancel things here unless you can find a common factor in the top and the bottom. We can't factor either of these things. We probably can't do any algebra to simplify it. We also can't do a u substitution here. The only reasonable choice for the u here would probably be the bottom polynomial, that 14x squared minus 6x plus pi. But we have enough experience with u substitution now to realize that the only way that's going to work is if the derivative of our u is also being multiplied in our integrand. And it's not. You'd have to have the derivative of the bottom showing up precisely on the top in order for this process to work. And it doesn't. The derivative of 14x squared minus 6x plus pi is 28x minus 6, and that is not appearing on the top. It's not even a factor at the top. So u sub isn't going to work. Algebra isn't going to work. Our other techniques, trig integrals, trig substitution, integration by parts, probably are not very promising in this situation. So what do we even do? Well, let's think about what kinds of rational functions do we already know how to integrate. There are a few of them. There's one kind of rational function that we know how to integrate very easily, and that's polynomials themselves. Remember, every polynomial is a rational function, just like every integer is a rational number. This polynomial here, 3x to the fifth plus 1/2 x cubed minus 8, is the same thing as that whole polynomial over 1. And since 1 is also a polynomial, that's automatically a rational function. So there's a whole class of rational functions that we already know how to integrate. And let's actually find the antiderivative here. So this is just, well, I'm going to raise the power by 1. That's going to be x to the 6th. Going to divide by 6, and we're also multiplying by that coefficient of 3. Plus, well, we've got 1/2 of whatever's next. We're going to have x to the 4th power, again, raise the power by 1, and we'll divide by 4. Perhaps I'll just write it right here, times 1/4, just to keep my constants together, and minus 8x. And of course, plus a constant. So we can just simplify that. That's pretty easy. 3/6 is 1/2, so we've got 1/2 x to the 6th plus 1/2 of a 4th, that's 1/8 x to the 4th minus 8x plus a constant. Very simple. And any polynomial at all, any sum of powers of x's, integer powers of x's, with maybe some coefficients that are just numbers, any polynomial at all can easily be integrated because we've known since the very beginning how to find the antiderivative of a function like that. So we're all set. Let's make a list of which rational functions we know how to integrate. Polynomials, easy. We know how to handle all of them. Our next case of rational functions that we know how to integrate are ones with a constant top and a linear bottom. Let's take the very simplest example we can think of right now. let's find the integral of the easiest constant, which is 1, over the easiest linear function x times dx. Well, the integral of 1 over x dx, we just know that antiderivative already. That is the natural log of the absolute value of x. Don't forget that absolute value there. And, of course, plus a constant. So what happens if we try a slightly more complicated one? Let's try this one. How about the integral of 7 over 5x minus 1 dx? Well, that's not actually too bad. Let's try a u substitution here. Let's let u equal 5x minus 1. The derivative of u is du, and the derivative of 5x minus 1 is 5 dx. So we'll have to divide by 5, and we'll get 1/5 du equals dx. Notice, any time that our u is a linear function, it is a number times x plus a number, of course plus -1 here, any time that our u is a linear function, the du is just going to be a number times dx. It's a very, very simple substitution here. A substitution that will always be successful. Okay, so we'll just do our substitution. We end up with, let's pull that 1/5 to the outside. We have the integral of, well, I could say 7 on the top, but actually let's just pull that 7 out as well. 7/5, and we have just 1 over our u times du. The 1/5 came from replacing dx with 1/5 du. And the 7 out front comes from just pulling that 7 that was on the top out to the front and leaving us with a 1 in the middle there. And we end up with 7/5 times the natural log of the absolute value of u plus a constant. And we'll just fill our u back in. We have 7/5 natural log of the absolute value of 5x minus 1 plus a constant. That is our integral. What if we try one more example here and just get the pattern? I want you to see that any time that we do a u substitution where the u is a linear function of x, the whole pattern is very simple. So simple that you don't actually have to write out the u substitution. Let's try a different one. Let's try the integral of pi over 19x minus 4 dx. Now, we could do a u sub here. The u would be 19x minus 4. And the only thing that would change about our answer is, well, let's just imagine that our 19x minus 4 is already the u. We have essentially 1 over that. The antiderivative is the natural log of the absolute value of 19x minus 4. Right? But we also have that pi on top. That's a constant multiple, goes along for the ride. But also, because of that u substitution, we're going to have to divide by the coefficient on the x, because the du will end up being 19 dx, and you have to divide by that number. So it's going to be divided by 19. And we'll just add a constant. We can do this entire u substitution without having to write it out. If you're feeling a little unsure about this, then you should take the steps to write it out. But you should work to see and understand and predict the pattern that's here, so that eventually you can save yourself some steps and some extra stuff on your paper and just work out the solution in this case here. You can do a u substitution when the u is a linear function of x without showing the steps. Now what happens if we look at a very similar rational function, a function that has a constant on the top and a linear function on the bottom, but that linear function is taken to a power on the bottom. Let's take a very similar one. Let's find the integral of 7 over 5x minus 1 to the 10th power times dx. Well, we can do a u substitution here too. Let's let u, again, u should always be the function inside a function, or the function that has something else happening to it. Let's let our u be 5x minus 1. And again, our du is the derivative of this thing, is 5 dx. So we can divide by 5 and say that 1/5 du equals dx. Let's fill that in. This equals, let's see, again, maybe I'll pull my 7 out. I'm also going to pull that 1/5 out, so 7/5, and then I'll put my du here. So I've got dx is equal to 1/5 du. And what's left over here in our integrand here is 1 over u to the 10th power. So what do we do with this? Well, this is just a power function, right? We've got this is equal to 7/5 integral of u to the negative 10th power, because 1 over u to the 10th power means you're dividing by u 10 times. So you're u to the negative 10th power times du. And this is easy. We'll just find the antiderivative. We're going to get 7/5 u to the, let's see, negative 9th power. We have to raise the power by 1. We also have to divide by the new power, which is negative 9, and plus a constant. And we'll just bring this guy right over here. This equals, all right, let me deal with those coefficients now. So we've got a negative, right? Divided by a negative is the same thing as multiplying by a negative. And we've got 7/5, but we're also dividing by 9, so I can say times 9 on the bottom here. And then u to the negative 9, maybe I'll just write that as 1 over u to the 9th, just so I have positive powers, plus our c. And last step here is just to fill in what our u is. So this equals negative 7 over 45 times 1 over 5x minus 1 to the 9th power, plus a constant. So that was another easy u substitution. In fact, the u substitution was exactly the same one that we did when our denominator did not have a power. It's just that because our denominator has a power that isn't 1 this time, we don't end up with a natural log in our answer. We just end up with a new power function of u. And we can substitute back in our function of x. So what this tells us is that any time, any rational function that has a number on top and the bottom is just a linear function, a number times x plus a number, maybe that's raised to a power, maybe it's not, but it's a linear function, or something that you can factor so that you have a linear function to a power. Any rational function of that form, we know how to do the integral. We just need to do a u substitution if necessary, and it will be a very easy u substitution. So let's go back and add this to our list of rational functions whose integrals we know how to solve. So we know how to integrate polynomials, and also any function that has a constant on the top and a linear on the bottom, maybe one with a power. And we'll do a u substitution in those cases where whatever's on the bottom, ignoring the power, is our u. Here's our next case. What happens if we have a rational function whose denominator has a power higher than 1? What happens if we try to integrate a rational function whose denominator is quadratic, meaning the highest power on x is a 2? Let's first look at what we have with a constant top and a quadratic bottom. Easiest example, the integral of 1 over x squared plus 1 dx. So our top of our rational function is constant, and the bottom is quadratic because the highest power on x is 2. But this is easy. We actually know the integral of this already. This is not one that you could necessarily figure out from scratch, but we know the function whose derivative is 1 over x squared plus 1. That function is the inverse tangent function, arc tangent of x, or tangent to the minus 1 of x, plus a constant, of course. And again, these are two different ways of writing the same function. I prefer the first one, but you will see the second one showing up sometimes. It's just the inverse tangent function, that's all it is. So, what happens if we want a slightly more complicated one? Let's find the integral of 1 over x squared plus 9 dx. Well, it turns out we can solve this one by a fairly simple trigonometric substitution. I'm not going to go through all the details of that because I want you to try it for yourself. But what you'll find, you'll end up with, this is going to be 1/3 arctangent of x over 3 plus a constant. You might notice here that 1/3 of the x over 3 is maybe a little bit of a hint to you that you could actually solve this by doing a u substitution, letting u equal x over 3. And if you do that substitution correctly, you'll actually end up with a situation where you have a number times 1 over u squared plus 1, and you can actually just use that identity. In general, here's the general formula here. The integral of 1 over x squared plus a squared. A can be any number, doesn't even have to be an integer, but x squared plus a squared dx is always going to be 1 over a arctangent of x over a plus a constant. Again, you can work this out, you can prove this for yourself using a very simple trig substitution. Let x be equal to a tangent theta, and you'll find that works. And that might be a hint to you. It may explain why arctangent is actually showing up in the answer here. What happens if you've got another number on top, a different constant? Let's say you have a different constant on top here. Let's call it, well, I can't call it c because I'm already using c. Let's call it b. Well, the only difference is you're just multiplying the whole thing by b, so we're going to end up with a b out front here. That's the only difference, right? So we now know how to find the integral of any function of the form a number divided by x squared plus a number squared. Now, if there's a coefficient on the x squared, you can deal with that by trying to factor out that coefficient and just do a bit of algebra to rewrite the whole thing as some coefficient in front of the whole function and have a function where the denominator does not have a coefficient on the x squared. What do you do if you have a linear term in here? What if you've got something where it's like plus cx plus a squared? What if you have an x term showing up in there? We're not going to talk about explicitly how to do this, but your textbook does discuss it a bit. There's a method you can use called completing the square that will allow you to rewrite that whole denominator as something resembling x squared plus a squared, and you may have to do a very minor u substitution to turn it into a form that you actually want. So there is a way to handle the situation where you don't have a perfect sum of squares. You may have a linear term in there, but there's a way to rewrite it. So in general, we're all set for our purposes. We know how to integrate polynomials. We know how to integrate functions where you have a linear function on the bottom, that is x to the first power, with a constant on top. And we also know how to integrate functions that have a constant on top and a quadratic bottom. And again, I've not shown you every possible case here, but I've shown you the sort of the basic case that you could work through. Everything else is based on this. Our final case to look at here is a situation where you have a quadratic function on the bottom. In fact, I'll just work with a sum of squares or an x squared plus a constant, the same way we had in the last case, and an x on the top. Let's take an example. Let's find the integral of x over x squared plus 9 times dx. Well, in this case, you might try a trig substitution, but there's always another easier method you should try first. Remember, going back to our initial discussions of solving integrals, the first thing you should always try is doing some algebra. The second thing you should try is a u substitution. And that's what we should try here before we start getting into trig substitution or any other fancy techniques. Let's just do a u substitution. Let's let our u be the function on the bottom, that is x squared plus 9. So our du is the derivative of this. Du equals 2x times dx. And guess what? We're in luck. There's an x times dx showing up in our integral, right? The x is on top, the dx is on the side, but really the dx is on the top. We could divide by 2, cancel those out. That's easy enough, right? So this equals 1/2 integral of du over u, or 1 over u du. So again, we end up with a 1/2 natural log of the absolute value of u, plus a constant. And we'll just fill in our u. We end up with 1/2 the natural log of the absolute value of x squared plus 9, plus a constant. Now, it turns out in this particular instance, we don't actually need those absolute value signs, do we? Why not? Well, whatever x is, whether x is positive or negative, x squared is always 0 or higher, right? Even a negative number squared is always positive. And if you add 9, then the x squared plus 9 is always positive. It's always greater than 0, which is good because we can't plug 0 into the natural log function anyway. So x squared plus 9 is always a positive number, which means the absolute value signs are doing absolutely nothing. They are never turning this thing positive because it's already positive. So you can get rid of the absolute value signs here or keep them. I don't care which. But what should we do if we have a coefficient in front of the x? Say we have some number times x. Maybe we've got a 3x on top here. Well, that's easy. That 3 is just going to go along for the ride, right? The 3 is going to be here over the 2, which means it's over here, which means it's here, and your 3 just gets multiplied by everything else, right? Your u substitution does not change. In fact, nothing else changes about this process. So you can have a number times x on the top, and you'll still be able to solve the problem, and it will be just as easy, right? So let's add this to our list of cases that we know how to solve. We know how to integrate rational functions that are polynomials, or that are ratios that have a constant on the top and a linear bottom, maybe a linear bottom to some power. We also know how to deal with a constant on top and a quadratic bottom, specifically if you have a sum of squares on the bottom, so that there's no linear term, there's no x term. But again, there is a technique for handling that. We're not going to discuss it in this class. And we also know how to handle a case where there is an x on top and a quadratic bottom. In fact, these last two cases together actually mean that we can handle anything that has a linear top and a quadratic bottom. In other words, you can have any linear function, a number times x plus a number, divided by an x squared plus x plus a number, let's just say. So actually, in general, this is kind of the thinking that we need to have here is anytime you have a rational function where the degree of the polynomial on top is less than the degree of the polynomial on the bottom, you might be able to solve it. Maybe we can find a method of solving it even when the degrees are both higher than we have in this list here. And that's exactly what we'll do in the next few videos.